Let's look at the evens, shall we? Number 58. Part A is negative 6x. Part B is potential energy is negative 6x plus 24. Part C, the potential energy is negative 6x plus 50. 59 was in the back. Number 60. Mass 1 is 5.68 kilograms. Mass 2 is 4.32 kilograms. The next even is 62. Part A, the force is negative 4ax cubed. Part B, the force is 0 when x is 0. And the last question, 64. What did they want? 64. A graph? Sketch this. All righty. So let me show you what the graph looks like. It should look like this. So here is our force versus our position. Horizontal line. It's frozen. Thank you. We get a horizontal line at 2. Then we get a diagonal line, negative slope, and then another horizontal line at negative 1.4. The diagonal line with the negative slope begins at a position of 2 meters, and the horizontal line here at negative 1.4 newtons is at 3.5 meters. That's your graph. All right, what do you guys want to go over? Ruben.
60.
Number 60. I know we love these Atwood's machines. Well, guess what you're going to see on your AP exam? An Atwood's machine. There is always at least one. So it's something we got to practice. And if you need more practice with Atwood's machines, you should look back at the packets that I posted for review with chapters 4 and 5, the PDF files that are there. Mark, let's take that internet-connected watch off and stick it in your backpack, please. It's on the list of prohibited devices from bell to bell for the day. All right, number 60. So here is mass 1, and here is little mass 2. And it tells us that they're going to start from rest. We know after 3 seconds, they're both going to be moving at 4.0 meters per second. And at that time, the kinetic energy of the system is 80 joules, and each has moved through a distance of 6.0 meters. I want you to determine the values for mass 1 and mass 2. All right, so to do this, I'm going to start with free body diagrams for each of these. I know that mass 1 is going to have its weight pulling it down, which is M1G, and a tension force pulling up. This is going to have the same tension force pulling up and a smaller weight pulling it down, which means that this will accelerate up, this will accelerate down with the same thing. Now, what I'm going to do is treat this as a system where I can get rid of the tension. The pulley at the top is there to change the direction of the tension. Yes? Which means if I look at a system, and I'm going to kind of draw it sideways, I would have, if I move this so that way these forces are now pointing at each other, this weight would be pulling this way. I'm going to show you another way to do this, and this was described in one of the videos in AP Classroom that I asked you to watch for the last unit. There's that tension, and there is FG2, which is M2G. We know the whole system is accelerating that way. See what I just did? Okay. Everybody follow what I'm doing? Now what I'm going to do is I'm going to treat this as a system to get rid of that tension force, because now it's a Newton's third law force, action-reaction. These forces are going to cancel out, which means that the net force on this system would be this force minus that. And that's got to equal the mass of the system times that acceleration. Is everybody with me? You see how you can do that? That happens because those two forces cancel out in the system. And what is the mass of the system? It's mass 1 and mass 2. The net force would be this minus that. That gets rid of one unknown right away, which is the tension. So I can speed up the problem, and I don't have simultaneous equations to solve, except the fact that I don't know the masses. So m1g minus m2g is equal to m1 plus m2 times a, or if I factor out the g, it's m1 minus m2. And now what I'm going to do is I'm going to solve for a, or actually, I'm just going to leave it alone. I know what a is, and I can get a from the data that was provided to me. I know that the initial speed of my system is 0 meters per second. I know it ends at 4 meters per second. That happens in 3.0 seconds. And I know that the displacement is 6.0 meters. So the first thing I'm going to do is I'm going to figure out what is the acceleration here. So to do that, you've got a number of options to do that. I'm just going to use the change in the speed over the time. That is 4 meters per second minus 0 meters per second over 3.0 seconds. So 4/3 is my acceleration. So I'd have 9.8 meter per second squared is mass 1 minus mass 2. And this is mass 1 plus mass 2 times this 4/3 meter per second squared. Now, I do have two unknowns, which means I do need another equation to help eliminate, and that's going to come from the kinetic energy. You are told that the kinetic energy of the system, which can be found with that equation, ends up being 80 joules. So 80 joules is 1/2 of the sum of these masses times the 4 meter per second speed squared. 4 squared is 16. Half of that is 8. So 80 divided by 8 is 10. So I know that 10 is mass 1 plus mass 2. There's mass 1 plus mass 2. You with me so far? Do you all see how I can just change that out? Mass 1 plus mass 2 is just 10. Okay. So now let's see if we can get rid of one of these from here. Which one do you want to get rid of? 1 or 2? Okay. So we're going to get rid of mass 1, which means I'm going to change mass 1 to 10 minus mass 2. So 9.8 times 10 minus mass 2 minus mass 2 is 10 times 4/3, which is 40/3. I'll just write it as 40/3. So this is 9.8 times the quantity 10 minus 2 times mass 2. Can you solve that for mass 2? Oh gosh, I hope so. So 10 minus 2 mass 2 is 40/3 divided by 9.8. Now, negative 2 m2 is 40/3 divided by 9.8 minus 10. So divide by negative 2. So 40/3 over 9.8 minus 10. And all of that is over negative 2. All right, so go to your calculator, type that in. So 40 divided by 3 divided by 9.8 minus 10, divide that whole thing by -2, tells us that mass 2 is 4.32 kilograms. So what is mass 1? Mass 1 is 10 minus that. So that means mass 1 is 5.68 kilograms. Okay? Make sense? All right. Anything else you want to go over? Nick?
Go back up to like the
Do you need me to go up further? You need me to explain anything? You're good? Okay. Matt? You have to do that in order to get the acceleration for the system. There's no other way. But you are not solving using, your final answer isn't using a kinematics approach to get these masses. You're only doing that so you can get the acceleration of the system. There's no other way to get the acceleration of that system. No other way. They gave you kinematics data, so you have to do that to get the acceleration. Anything else, Jerry? Sure. Let's look at 63. '63 on page 180 says that we have a potential energy function. We use capital U for potential energy, is given as C over X, where C is a positive constant. I want you in part A to find the force as a function of X, or F of X. What is F of X? Okay, I have to rewrite this in order to be able to come up with my answer. Whenever you divide by something, it's the same as multiplying by that variable to the negative power. And that's -1, right? Because that's x to the first power. Now I can get my answer to this because I should recall how to get a force from potential energy as a function of position. Force is the negative derivative of the potential energy with respect to position. I believe that's on your reference table. Either that, or they tell you that the potential energy is the negative integral of the force with respect to position. One's the integral, the other one's the derivative. But you have to remember it's the negative of it, which means that we're going to do the negative derivative with respect to position of C times x to the -1 power. You remember how to do derivatives of this? What do you do to get the derivative of that? Don't even worry about the negative sign yet. How do you get the derivative of this? Ruben? So you're going to add or subtract 1 from the power. Subtract 1. And now I got to keep a negative out front because that's the derivative. And then I need to negate it. Negative times negative is positive. And what is -1 minus 1? -2, which is another way to say that the force is C over X squared. Okay? You all right with that? Okay, let's now look at part B. Part B says, is this force directed toward the origin or away from it? So Is this force directed toward the origin or away from it? I want you to think about this for a minute. Is this force function ever going to be negative? It's always going to be positive. That means it's going towards the origin. That's what that means. It's going towards the origin. As long as we're not at an x value of 0. Because if you're at an x value of 0, what's the force? If the x is 0, what is the force? No, it can't be 0. If the x is 0, what's the force? Undefined, infinite, huge, massive. All right, part C. Does your potential energy increase or decrease as x goes up? So think about that. As x approaches infinity, what's going to happen to this force? Is it going to get bigger or smaller? It's going to get smaller. So it's going to decrease. If you were to make a graph of that force with respect to position, you're going to see a hyperbola where it is approaching 0 as the x goes up. Now, part D, answer parts B and C where C is a negative constant. Okay, so if this constant is negative, is the force going to be positive? Okay, you guys are like looking at me like I have two heads. Yes. Oh, yeah, because it's positive. Positive means away, to the right, right? This is always a positive thing. It's always in the first quadrant. You can't get negative. Well, even if you were, it's, sorry. This is away, which means that if it's negative, if you have a negative constant here, then what's the force? It's always negative, which means it's now going towards. So if X or if C is negative, F of X is negative. So this would be towards. We're talking about first quadrant. We're talking about first quadrant. You'd have a negative force, which would be pointing to the left. And then they ask you for the second part, part C, if X goes up, but C is negative, what is going to happen to your force? Can you tell me? Is it, well, what's your graph going to look like? Here's your force. Here's your position. Where are we going to be on this graph? Above a 0 force or below it? Below it. So as X gets bigger, this force still needs to approach 0 in this way. So this means, wait a second, I was looking at, I didn't answer part C, did I? I'm not answering the right question. Part C says, does the potential energy increase or decrease, not the force? Okay, we know that the force is approaching 0, but what happens to our potential energy? Remember that your potential energy is C over X. So if X is approaching 0, or I'm sorry, approaching infinity, what is the potential energy approaching? Still approaching 0. If I do that in part D, where now the potential energy is negative C over X, as X gets bigger, what is the potential energy going to approach? Still going to approach 0. but it's below the axis, right? Because we have a negative. It's going to be below, so that is an increase. Because you're going up on the graph. Okay. Yep, Matt.
I don't understand. What does it mean going towards the origin?
Here's an object on the position axis. Is the force this way, where the position of 0 meters is here? There's your origin, or is it going that way? Which way is the force directed? Since your force is going to be positive direction on the horizontal axis is to the right. That's away from the origin, an initial position of 0. If the force is negative and you're here, that means it's directed toward the origin. Okay, that's a positive direction. That's your negative. And your origin is here at 0 meters. Okay. Anything else on the assignment? You are okay with 64, Nick? 58, yes. Let's go back to 58. In question 58, they tell you that we have a force, a constant force of 6 newtons. And I want you to find the potential energy function in part A for some arbitrary initial position where this initial potential energy is 0. Okay. So I'm going to rewrite this force as a function of position. Even though it's constant, I can write it with the position. The force would be 6 times x to the 0 power. What is x to the 0 power, folks? It's equal to what? 1. Okay, so there is that force function. How do you get potential energy? It is the negative integral of the force function with respect to position. So we're going to take the negative integral of 6 times x to the 0 power with respect to x, which means I'm going to have negative 6x. We add 1 to the power and divide by the new power plus a constant. So this is the same as 6x plus a constant, but this helps you determine what your constant is. We're saying when we have this arbitrary initial position, we have to get a value of 0 for the potential energy. So what is that value here? It means when I plug in x0 that this must equal 0. So what does that constant equal? Negative 6x0 is what it equals. So the potential energy as a function of position is 6x minus 6x0. I think I said just negative 6x, right? Because I'm assuming that x0 is 0, but it's not technically. If x0 is 0, then the potential energy is just 6x. Would that make sense? Because then I would plug in 0 for this. 6 times 0, 0 minus 0, it's gone. Gentlemen. All right. But this is the more generic function. Now let's go to part B. Part B wants you to find the potential energy such that the potential energy is 0 at 4 meters. So we know the generic formula for the potential energy is 6x plus c. But now they're telling you that when X equals 4 meters, that the potential energy is 0. So we're basically now figuring out what is the constant now. So we're going to say that 0 is 6 times 4 plus the constant. So what is the constant now? Negative 24, which means that the potential energy as a function of position would be equal to 6x minus 24. You good so far?
Yeah, I found out.
What you did?
Yeah, because I didn't have it as the negative, and that only affected the signs in the first two answer, but it made the C value wrong in the third answer.
Tony has that you said negative 6x plus 24, and then I changed it.
Did I forget the net? Well, no. I forgot the negative there, didn't I? Negative, sorry, negative. So this is negative. So that's positive. So this is plus.
Yeah, because originally I
Sorry.
six.
My mistake. I dropped a negative sign. So this is plus 24. 6x plus 24. Negative. Out front, yes. Negative 6x plus 24. And then you would do the same thing in part C, which asks you if we're at 6 meters and the potential energy is 14, what's the constant? You're going to do the same idea. Okay. Yeah, my mistake. I just dropped it by mistake from here to here, which then affected the sign of everything else. And this is, oops, that negative has to be there too. Okay. Anything else? Yep. '64 says on the potential energy curve for the potential energy versus the position Y shown in figure 640, where the segments A, B, and C, D are straight lines, sketch a plot of the force versus the position. All right. Remember how you get force from potential energy. Remember that force is equal to the negative derivative of the potential energy with respect to position. What is a derivative on a graph? It's the slope, right? So we're going to do the negative slopes. The negative slopes. So they tell you on this graph that A to B is a straight line, and so is C to D. So you can get those slopes. Let's do that. So what is the slope from A to B? I'm going to do the change in the Y over the change in the X. From A to B, that means my Y value ends at 2, starts at 6. The X is ending at 2, and starting at 0. So that is negative 4 over 2. So the slope is negative 2, which means that the force from A to B is not negative 2. It's got to be the negative of that. So it is a constant value of positive 2 newtons. It's not changing anywhere between there. It's got to be a positive 2 newtons. Let's now figure out what the slope is from C to D. Change in Y over change in X. The Y value ends at, what did I say that was? I said it was around 5.5 joules, and it starts off at 2 joules. The X value ends at 6 meters, and I said it starts at roughly 3.5. So if I work out that slope, I get about 1.4, which means that the force from C to D is a constant negative 1.4 newtons. So now if I make my graph, sketch it from force versus the position. And they're using the letter Y for position instead of X. That's fine. Who cares? I'm going to have a value that starts at -2. No, I'm sorry, +2. There's my force. Starts +2. And it will be +2 until I get to a position of 2 meters. Let's say 2 meters is here. Then I know from C to D, I need a force value of -1.4 newtons. And that's going to start 3, 4, 5, 6. So it's going to start at roughly 3.5 and end at 6. 3.5, 4, 5, 6. Which means that between this, that's where we get our diagonal line. We just connect those 2 points. Okay? And that's how we get it. Does that make sense? Remember, derivatives are slopes. Matt?
Is it correct if that's a curve, like, coming from there to
You mean from here to here? How are you going to curve it?
like it's very
Anything else? Okay. So for Monday, we have to get assignment 33 completed. And this is your last textbook one for chapter 6. Questions 65 to 70. 65 to 70. There are 6 problems for chapter 6 due Monday. 65 to 70. Okay? Then on once we finish that, going over that on Monday, I'm going to talk to you about the next lab. And on Tuesday, you're going to be collecting data for your next lab. So Monday night, I'll ask you to read through the lab, but I'll discuss it with you first on Monday. Okay, and it will take us about 1.5 days to get all the data. So we'll start getting it on Tuesday. We'll finish it another day when we're working on chapter 7 stuff. Okay? All right. And I would also encourage you to start working on those videos. All right. And those videos are for chapters 6, 7. All right. They even did this. My daughter goes, Mom, you got to do it this way. I'm like, okay. And she told me something else silly to say. And I'm like, no, I'm not going there. That's